We begin at the operational baseline, online transaction processing, or OLTP. These systems are optimized for rapid day-to-day data entry, millions of these individual short-term records together to build a permanent historical archive. This environment requires online analytical processing, or OLAP. OLAP creates an immediate architectural tension. Instead of writing single rows quickly, these systems must execute read-heavy queries that scan millions of records simultaneously to calculate long-term aggregate trends. Forcing a system to dynamically calculate these massive trends row by row creates severe latency. The sequential scanning process simply takes too long, causing query execution timers to time out and fail. This latency establishes a core constraint in data warehousing. You must trade granular storage scalability for query execution speed. Two primary models emerge to handle this constraint. The first is relational OLAP, or ROLAP. It prioritizes deep, highly scalable storage at the expense of query speed. The opposing approach is multidimensional OLAP, or MOLAP. It guarantees instant query speeds, but sacrifices deep storage capacity to get there. Modern enterprise analytics require both. Here we see the divide. On the left is the flat, two-dimensional relational table network of ROLAP. On the right, the solid, three-dimensional geometric data cube of MOLAP. To bridge this divide, engineers developed hybrid OLAP, or ALAP. To understand the mechanics of HOLAP, we must first mathematically deconstruct exactly where and why the physical structures of ROLAP and MOLAP fail on their own. ROLAP relies entirely on traditional relational database engines to house analytical data. This animated diagram illustrates its core design pattern, the star schema. A central fact table sits in the middle, connecting outward to a series of surrounding dimension tables. The central fact table stores measurable metrics, like total revenue or units sold. The surrounding dimension tables hold descriptive context, used to filter those facts, like store locations and product categories. Because this is a standard relational database, ROLAP can scale indefinitely. It easily retains complete item-level transactional logs spanning decades. The critical weakness lies in the computational workflow. The ROLAP engine performs absolutely zero pre-calculation when data is loaded into the warehouse. When an executive dashboard requests an analytical summary, the database engine must build the answer from scratch. The engine is forced to dynamically execute complex SQL statements, resolving nested joins and group-by clauses on millions of rows simultaneously. While ROLAP guarantees total data detail, its reliance on on-the-fly computational physics makes it structurally incompatible with instant dashboard reporting. MOLAP abandons relational tables entirely to solve this latency problem. It introduces a new structure, proprietary multidimensional arrays. In this diagram, we see a 3D geometric matrix known as a data cube. As incoming data flows into it, specific internal interceptions light up with coordinate values representing business metrics like region, product, and time. The advantage comes from pre-calculation. During the initial data load phase, the MOLAP engine computes and stores every possible dimensional summary and aggregated intersection. As a result, dashboard queries are executed instantly. The engine does not calculate anything on the fly, it simply fetches the pre-computed answer. But this design introduces a mathematical flaw known as the sparsity problem. Adding new business dimensions causes the total volume of the cube to grow exponentially. Because not every product is sold in every region on every single day, vast sections of these new intersections contain absolutely no data. These empty intersections still reserve memory, wasting massive amounts of physical disk space on blank coordinates. Because of this sparsity problem, MOLAP cubes face severe capacity limits. They simply cannot store deep item-level transaction logs without exhausting system storage. Hybrid OLAP acts as a unified routing and storage tier, segmenting data based on predictive usage patterns. This architectural structure diagram shows the HOLAP mechanism. The central data pipeline splits, with the upper flow routing highly summarized, frequently accessed aggregate metrics directly into a 3D MOLAP cube. Dashboards query this upper layer exclusively for their reporting, securing the instant speed of MOLAP. Meanwhile, the lower split of the pipeline routes the dense, raw transactional records down into relational backend tables. This split enables a seamless action called a drill-down query. When an analyst spots an anomaly in the high-level summary, they click to investigate. The HOLAP engine bypasses the cube entirely and drops their query directly into the granular relational tables to extract the specific transaction logs. Keeping the heavy transaction logs securely inside the relational database ensures the multidimensional arrays remain small and highly performant. In this way, HOLAP neutralizes MOLAP's sparsity problem with relational depth, and it neutralizes ROLAP's latency problem with multidimensional speed. In systems engineering, structural perfection is never free. The primary drawback of HOLAP is its high architectural complexity. This zoomed-out view of the HOLAP structure visualizes the engineering burden. Forcing two contradictory database paradigms to operate as a single logical unit requires complex syncing pipelines, represented here by these flowing data packs and turning gears. These syncing pipelines are notoriously fragile. They must operate flawlessly during overnight extract, transform, and load, or ETL, windows. If these synchronization pipelines fail, the high-level dashboard summaries in the cube will no longer mathematically match the low-level relational facts in the tables. HOLAP successfully solves a user-facing data limitation, but it does so by transferring that exact weight into a back-end engineering and maintenance burden. Managing dual storage structures also demands specialized software licenses and significantly heavier compute hardware. The architectural decision matrix is strict. Rely on ROLAP for infinite detail, deploy MOLAP for absolute speed, and implement HOLAP only when the business requires both. Analytical queries enforce a structural conflict between the depth of the data and the velocity of the answer. Data warehousing is the science of managing these compromises. As illustrated by this heavily engineered bridge connecting two megastructures, true enterprise optimization does not come from finding a flowless system. It comes from engineering the strongest possible connection between opposing physical limits.